Hi, welcome to Harvard Applied Math 205, a graduate course in scientific computing and numerical methods. I'm Chris Rycroft, and in this video we're going to look at underdetermined least squares problems. We're going to look at cases where we're trying to fit functions that have more parameters than we have data points, and we'll look at the ways that we can regularize problems like this to get unique solutions. So far, we focused on over-constrained systems, where there are more constraints from data than we have parameters in our model. But we can actually apply the least squares methods to under-constrained systems as well. And suppose now that we're looking at an under-constrained system, AB equal y, and here A is an m by n matrix, and in this case, m is less than n. So if we write out this system, then we end up with a short wide matrix A, a long parameter vector B, and a short vector of data y. So if we now try and apply the least squares methods to this system, then we first write down phi of b is equal to the square Euclidean norm of the residual. And so that would be then the square Euclidean norm of y minus ab. And we could apply the same arguments as before, setting the gradient of phi equal to 0. And we'll arrive again at the normal equations, A transpose AB equal A transpose y. But in this case, we know that our matrix A transpose A can have rank at most m, and here m is less than n. And that tells us then that the matrix A transpose A has to be singular. And typically, that would then tell us that there could be infinitely many solutions for the parameters b that would set our residual equal to 0. So we want to be able to have a method then that could actually just select a particular one of those possible solutions. So the first idea is to pose a constrained optimization problem. So here we could find a solution B that minimizes the 2 norm B transpose B, subject to the constraint that AB equal y. And this is possible, and it can be treated using Lagrange multipliers that we'll cover in the optimization section. So the idea then is that the constraint restricts us to an n minus m dimensional vector space, and in that subspace we can then search for this unique solution that minimizes B transpose B. And we'll show later that if we use Lagrange multipliers, then that unique B actually satisfies A transpose times A transpose inverse of y. And as a result then, for the underdetermined case, we could actually generalize our pseudo-inverse definition and say that in this case, when you have more columns than rows, we could actually define then that our pseudo-inverse is equal to A transpose times A transpose all inverse. And here we actually note that the previous behavior of the pseudo-inverse is actually reversed. So now we see that A times its pseudo-inverse is equal to the identity, but in general, the pseudo-inverse times A is not equal to the identity. So here, the pseudo-inverse becomes what we refer to as a right inverse. So we'll revisit this problem when we get to the optimization section. But here we're going to consider an alternative approach for solving the under-constrained case. And the idea here is that we'll modify phi to obtain a unique minimizer. So we'll generalize our phi so that it has the square Euclidean norm of our residual plus the square Euclidean norm of a matrix S multiplied by this parameter vector B. And here then, we refer to S as a scaling matrix. And the idea here is that we're actually doing regularization. So we're trying to make the problem more well posed by modifying our objective. So now we could follow through the same steps that we did to derive the normal equations, and we actually find now that if we did this, we would end up with the following system. A transpose A plus S transpose S applied to B is equal to A transpose Y. And we need to now choose our S in a way that can ensure that this matrix A transpose A plus S transpose S is invertible. And you can actually prove here that if S transpose S is positive definite, then this matrix A transpose A plus S transpose S will be invertible. And the simplest choice that we could therefore do would just be to set S is equal to mu, some constant, multiplied by the identity matrix. So we'll now demonstrate this using a Python example underscore lfit.py that fits a degree 11 polynomial to the function y equal cosine 4x. And we'll use 5 data points here that are equally spaced over the range from 0 to 1. And so here then, we've got 12 parameters and only 5 constraints, and therefore we're dealing with an under-constrained system. And our matrix A in this case will be 5 by 12. And here we're expressing our polynomial in terms of the monomial basis. And similar to the previous case we looked at for linear least squares, there's limited advantage to using Lagrange polynomials in this case. So if we try and calculate the condition number of the matrix A transpose A, then it works out to be 4.78 times 10 to the 17. And essentially, this is telling us that our matrix A transpose A is singular, just as we expect due to its rank deficiency. And this value that we get, around 10 to the 17, essentially tells us that we're seeing rounding error. And we expect that we'll get rounding errors on the scale of machine precision. And so this value is really working out 1 over machine precision. And if we ever see condition numbers of this scale, then essentially our numerical routines are saying that to within rounding error, this matrix is singular. So we'll now look what happens when we solve this problem using several different choices of regularizer. We'll now take a look at the underscore lfit.py example that demonstrates solving an underdetermined least squares problem. And we'll look at fitting a degree 11 polynomial that has 12 free parameters. And we'll first describe this function vand underscore f that will evaluate this polynomial at a position x for a given parameter vector b. And it will do this using Horner's method that we described in previous videos as an efficient method to evaluate polynomials. So we'll then go ahead and construct our data. We'll make use of 5 linearly spaced points from 0.2 to 1. And we'll go ahead and construct our Vandermonde matrix for this case, where we pass in our data points and then this optional argument that passes back a rectangular matrix that will now have 5 rows and 12 columns. And we'll set our corresponding y values just based on cosine of 4 times x. So we'll now look at 2 different methods to solve this underdetermined system. And we'll first look at using Python's least squares routine, the lstsq function. And if this function is passed an underdetermined system, then it will return the solution to the constrained minimization problem. It will find the solution b that satisfies the constraint ab equal y while minimizing the norm of the parameter vector b. And we'll call this and store the solution in b1, and we'll then calculate how well our fitted polynomial matches our 5 data points. In the second approach, we're going to solve the system using the normal equations plus the regularizer that makes their normal equations non-singular. And we'll use mu equal 0.05 for the strength of the regularizer. We'll go ahead and construct the matrix A transpose A that we need to solve the normal equations, and we'll take a look at its condition number. And we'll also now solve the resulting regularized linear system where we've incorporated this regularizer of mu squared times the identity. And again, we'll see how well the fitted polynomial matches the given data points. Finally, we'll plot our 2 solutions in relation to the data. So let me go ahead and run this program. And so we see here that if we look at the results of the LSTSQ routine, then this matches the data points exactly. And all of the data points exactly aligned here with the orange curve. And that is confirmed by the norm of the residual here, where we see that the residual is basically on the scale of machine precision. So when we look at the normal equations with the regularizer, we see that we still match our data points fairly well, but as expected, they don't match the data points exactly. And we find that in this case, there is an appreciable residual norm here. And if we varied the size of this regularizer, then we would see how that residual would change in scale. If we made the regularizer larger, then that would mean that we were more strongly imposing the regularizing term and correspondingly weighting the linear system solve lower, and in that case then we would see that the norm of the residual would actually be higher. Let's recap some of the results of our Python example program. So in the first case here, we're going to look at when s is equal to 0.001i, and in this case we're only applying a small amount of regularization, and this means that when we solve the problem, the main term coming from A transpose A will be dominant, and that means then that we will be matching the data points preferentially. So indeed, if we plot the resulting polynomial, we see that it goes very closely through our data points. And the residual, in this case, is around the scale of 10 to the minus 4. And in this case here, the magnitude of our parameter vector is around 4.4. We actually find that in this case, the condition number for our matrix A transpose A plus S transpose S is still around 10 to the 7. And because we only applied this very small amount of regularization, we're still dealing here with a matrix that is rather poorly conditioned. So let's now try a different case where we increase the regularization strength and we put in that s is equal to 0.5i. So in this case, we're strongly penalizing large B at the expense of the fit to the data. And indeed, if we plot the resulting polynomial, we see now that there is an appreciable difference between it and the data points. In this case here, the magnitude of R of B actually works out to be 6.6 times 10 to the minus 1. And in this case, we've actually significantly reduced the magnitude of the B vector to now 1.15. And in addition, the condition number of our matrix A transpose A plus S transpose S has now reduced to 62.3. So let's now look at a third case. Here, we're going to put that S is equal to a diagonal matrix where the first three terms on the diagonal are 0.1 and the rest are 10. And so here we are weakly penalizing quadratic terms and strongly penalizing any term above quadratic. And if we now look at the resulting polynomial, we see that it indeed looks rather like a quadratic, and we've strongly penalized those higher order terms. So our Python program can also solve the constrained case, and here we're going to satisfy our data points exactly, and our residual in this case works out at close to machine precision. And our B vector in this case works out as 7.18.